Welcome to springlib.
So here we have a diagram of our situation for our problem. So in this problem, we will let the angular speed at which the rod ABC is rotating, we'll let that be equal to omega for simplicity. We can see that we can treat C and A, gears C and A, as disks, each with radius r. The centers of each of these disks move with the same velocity in the opposite direction, the same speeds actually. So VA is actually equal to VC, VA bar is equal to VC bar, and this is BC, the distance between B and C, times the angular speed of rotation, omega. And this distance is 2 radii. From the center of B to the center of C is 2 radii to r, and that's multiplied by omega. And since gears A and C roll on the fixed gear B, the angular speeds for A and B, for A and C, are equal. Omega A is equal to omega C is equal to VC over R. And this is 2R omega over R. And so this is 2 times omega. So the angular speeds for A and C are twice the angular speed for the rod ABC. Now we'll use the principle of impulse and momentum as follows. Initially, the system has no momentum since it's at rest, so its angular momentum and linear momentum are both zero. Then the impulse of the couple is acting on the rod, and hence the forces, or the impulse QT, where Q is some force, acts on the center of disk C. So we're using the principle of impulse and momentum on disk C here. So at point C, we have impulse QT. At point D, which is the edge of disk C, we have an impulse PT, and that impulse is due to gear B, which is impacting on disk C. And the final system moves with angular momentum I bar omega C and linear momentum of the center of C, MC V bar C. So that's from our principle of impulse and momentum. So momentum is conserved in this situation. Now from here, we will take moments about our point labeled D. We will take clockwise moments about point D. So initially, we have no moments, the system's at rest, 0, plus when the impulse acts, we have Qt times R. And this is equal to our final momenta, or the final moments of the system about D, which is its momentum mc vc v bar c times the radius r plus the angular momentum of the center of the system I bar c omega c. So some of these we have values for, we can substitute them in. So this is q times t times r is equal to mc, and remember vc, v bar c, we wrote as 2r omega times r plus a half mc r squared to omega. So we're just writing in our values for each of these variables. And if we simplify this, we are left with q times t, our impulse q times t, is equal to 3 times the mass of disk C times r times omega. So we'll call this equation 1. We have too many unknowns here to solve for this. Now we'll apply the principle of impulse and momentum again on the rod ABC. So initially the rod is at rest, and hence it has no linear or angular momentum, both are 0. And then after the impulse, qt acts on point A to the right and at point C to the left, and our couple M and the impulse due to the couple MT acts on the rod. We allow the rod to start moving. And so the distance between A and C, remember, is 4r. Finally, about point B, the rod begins to rotate, and it has angular momentum I ABC, or I bar, which is the mass moment of inertia of the center, times its angular velocity omega. So the momentum and impulses are conserved. So if we did what we did before, we'll take clockwise moments like we did for disk A, but we'll take clockwise moments about B for the rod. And if we do this, we get that MT minus, well, the first term is 0 since the rod is initially at rest. For the impulse, we have MT minus QT times 4r. Remember, the couple M is already a force times a distance, minus QT, which acts at a distance of 4r, is equal to the final angular momentum, I bar ABC, times omega. So we can simplify this and write this as MT minus 4, and we'll bring QT together, times R is equal to 1 over 12. So we just, like before, we're just writing down our mass moment of inertia for the rod, 1 over 12 M ABC 4R all squared times omega. So we know what our mass moment of inertia is for a disk and for a rod. And this simplifies to MT minus 4 times QT times R, which is equal to 4/3 when we open out the square, times the mass of the rod M ABC times R squared omega. And we'll call this equation 2. So next what we'll do is we'll substitute for QT. Remember, we put QT together for a reason. Sub QT from equation 1 into equation 2. And what we get is MT minus 4 into 3 MC R omega times R is equal to 4 over 3 M ABC, the mass of the rod, times R squared omega. And so rearranging this, we get that MT is equal to 4/3 R squared omega into M ABC plus 9 times the mass of this C, 9 MC. And we'll call this equation 3. Now, before we substitute any values in here, let's write down our data to help us solve for couple M. What are we given? We are given that time t is equal to 2.5 seconds after the impulse. The radius of each of these disks is 2/12 feet. The mass of the rod MABC is equal to its weight, which is 4 pounds, over G, 32.2 feet per square second. We're also given the masses of disks A and C, which is, again, its weight, 2.5 pounds, over G, 32, that's not 3.2, 32.2 feet per square second. And finally, the angular rotation of the rod after the impulse is 240 revs per minute, which works out to 8 pi radians per second. Remember, one revolution is 2 pi radians. So if we go back into equation 3, so now we take our data from above and we substitute it back into equation 3, we get that the couple M, which we wish to solve for, into 2.5 seconds is equal to 4/3 into 2/12 feet squared times 8 pi radians per second into 4/32.2 plus 9 into 2.5/32.2. And from here, we can simply rearrange and solve. We just have one unknown. So M is equal to 0.3064 pound-feet. The magnitude of our couple is 0.3064 pound-feet. And therefore, our vector couple M is equal to 0.306 pound-feet in magnitude and clockwise in direction.